Thank you very much, and thank you everyone for coming and the organizers for inviting me. It's a great honor to be here. What I want to do today is is this too loud? Is it okay? Okay, so what I want to do today is try to convince you that Higgs bundles are something interesting to work on and study. And I'm going to do that by telling you what they are first and telling you about the moduli space, and then showing you some of the questions or perspectives that people are taking, and more precisely, the questions that I'm interested in looking at. And these are to do with Branes, so subspaces of the moduli space of Higgs bundles, and applications that these have within mathematical physics and other areas of mathematics, so representation theory or topology. So we're going to first start with Higgs bundles, give an introduction, and then go on into Branes and applications. There won't be any proofs of theorems or deep definitions. I'm going to give you more a hand-wavy version of the area, and you should stop me if you have any questions. Okay? All along, we're going to be working on a Riemann surface, so a genus, any genus bigger than 2, but a Riemann surface, a complex surface. So I'm going to fix it, and let me just put it here. I'm going to try to be write big, but you should tell me if I'm writing too small. So I don't know if this will work. So sigma will be a Riemann surface, and it will be fixed for now and for all, and it'll have genus at least 2. And we're going to work with Higgs bundles. Higgs bundles were introduced back in 1987 by Nigel Hitchin when he was studying self-duality equations on Yang-Mills self-duality equations on Riemann surfaces. So these are equations. These are differential equations whose solutions, if you were to take 4 dimensions or 3 dimensions, you get instantons or monopoles. But if you reduce them to 2 dimensions, the solution space gives you Higgs bundles. So that's the differential equation perspective. We're not going to do that. We're going to look at the geometry from there. So we're going to go directly into the definition of what Higgs bundles are, and then the properties of the moduli space and why people care about them. So the first definition, or the only definition I want to give you today, is what Higgs bundles are. A Higgs bundle is a pair E phi where we have a holomorphic vector bundle and a holomorphic section with values in one form. So for E, a holomorphic vector bundle on our Riemann surface, and phi is a holomorphic map that goes from E to E tensored with the cotangent bundle of the Riemann surface. So this is going to be holomorphic also, and it's what we call the Higgs field. So it's our Higgs map. Higgs field. So as an object, you can see that Higgs bundles are not too complicated. You have a surface, so any genus bigger than 2 surface that we have, that we can put here, we're going to have, for those that don't do this type of geometry, we're going to have on top of this surface a vector bundle, a vector space over each point of your surface, and the map, the Higgs field, is going to be a map that sends that vector bundle to the vector bundle tensor with the canonical bundle, the cotangent bundle of the Riemann surface, which means we can think of it locally as a matrix with values in forms, in differential forms. So let me give you an example of how this looks like. You could, in principle, since this cotangent bundle is a line bundle on your Riemann surface, let me call it K for simplicity. It has square roots, so I can fix a square root, and I can take K to the 1/2, and I can sum it up to its dual line bundle. So K to the -1/2. And I'm going to call this E. And we can produce a very canonical toy model to work with Higgs bundles. that we're going to look at as a matrix point-wise. Over each point, we have this vector space. So point-wise, I'm going to ask for the Higgs field to be a matrix that's off-diagonal. And when I have to think about how does it work, so for those that haven't worked with Higgs bundles before, you're trying to put this bundle, which is a rank 2 vector bundle, on the surface, and you're going to map it just from the definition to the same one. So k to the half plus k to the minus a half tensored with k. So this is what our matrix should do. And if I put here an omega and a 1, and I try to understand what does this mean, this omega point-wise is going to be sending k to the half to k to the minus a half. Sorry, this is k to the half, and this is a minus here. Right? K to the minus a half. How is it working? There we go. I put a first positive and then negative. So here and here, this is the omega, and the 1 is going to be the ones missing. So k to the half and k. And what you can see here is that this omega that sends k to the minus a half to its dual tensor with k is really a quadratic differential. So this omega is a quadratic differential on the Riemann surface. So it's a point in the 0th homology of the Riemann surface and k squared. So a quadratic differential. So this is a family of Higgs bundles, parametrized by quadratic differentials. So parametrized by quadratic differentials. And if you have heard of Higgs bundles parameterizing the Muller space, for instance, this is the family that parameterizes them in rank 2. So this is a very important family. It gives what people call the Hitching section. And the properties of quadratic differentials that parameterize the space becomes very important. This is what I want you to keep in mind when you think of Higgs bundles. You should keep in mind that there are matrices that act pointwise on vector spaces, and that we can do any linear algebra that we know, we can apply it to Higgs bundles. And there's one more thing that I want you to keep in mind, which is something that generalizes vector bundles. So if you are working with vector bundles and you want to put some group structure, you may as well just look at principal bundles for that group. And we want to do something similar. So I want to fix a complex Lie group. So let me put it here, GC complex Lie group. So I'm keeping here in yellow all the things that we're fixing, our Riemann surface and our complex Lie group, and I can define Higgs bundles for that Lie group, and it's going to be just a classical bundle with some extra conditions for reflecting the nature of the group. And that's in the case when the group, so for GC, the group, a subgroup of GL and C, we can define GC Higgs bundles. So we get GC Higgs bundles as simply these pairs E phi plus conditions E phi plus conditions given the nature of the group. So plus extra conditions. What do we mean when we say extra conditions? For example, if we took GC to be the special linear group, so SL and C, then what we would need to put as extra conditions would be that the determinant of the bundle as a vector bundle, so the top exterior power of the bundle needs to be trivial, so isomorphic to the trivial sheaf on the structure sheaf on our Riemann surface, and the trace of our Higgs field should be 0. If you were to put a symplectic group, then you'd need a vector bundle with a symplectic form and a Higgs field compatible. And before we move on, we can take a look at our example and see if we can spot any structure here. We notice that we have a line bundle and it's dual. So when we look at the topic stereo power here, the topic stereo power of E, this is going to be indeed trivial because it's the product of the line bundle and it's dual. And the Higgs field, of course, here is traceless. So trace is equal to 0. So we have a traceless Higgs field with a trivial determinant bundle for the vector bundle, which means our Higgs bundles here are actually SL2C. So it's a family of SL2C Higgs bundles parametrized by quadratic differentials. So this is all the definitions of objects that I wanted to have today. And from now on, we're going to be working with moduli spaces of these objects. Just like in the case of vector bundles that you can look on Riemann surfaces, you can look at moduli spaces by considering the good points, so taking away all the unstable vector bundles. And we can do the same here. We're not going to do it today, but you can get rid of all the Higgs bundles which are unstable for some definition of stability and construct a very nice moduli space, which will be what we're going to work with today. So let me put it here, remembering that we're going to just be working with pairs of a vector bundle and a section. I'm going to keep the example so that you have in mind what the objects are still. And what we're going to do is we're going to call MGC, so I'm going to put it here, trying to put it big, MGC, the moduli space of Higgs bundles. So this is the moduli space, and it should be with this stability condition that we're not mentioning. It's just like the one for vector bundles, but where you put a compatibility for the Higgs field of semi-stable GC Higgs bundles. And this space has many interesting geometry and topology that it carries, and that's what we're going to be studying. So let me give you a few reasons of why this space is interesting. This is a quasi-projective scheme, and it's most generally not smooth. So it's only smooth, for instance, if you took the general linear group, it would be smooth if the rank and the degree of your bundle were coprime, but otherwise it's singular. So understanding the singularizations or compactifications are questions that people are very interested in doing. And one of the properties that it has that's very interesting for us, and we'll carry on using it, is that it's hyperkähler. So remark, apart from being this quasi-projective scheme, whose dimension depends on the dimension of the group, it is hyperkähler. Hyperkähler. So there's going to be a lot of complex and symplectic geometry appearing for us given by this hyperkähler structure, and we're going to be using it a lot when considering branes inside the moduli space. But before we do that, let me give you a few more reasons to study this space. In particular, this space that was introduced back in '87 was also being studied by Simpson at the same time in his thesis, and soon later on by Donaldson and Corlett, and all together they allow us to see the moduli space of Higgs bundles as the space of representations of fundamental groups of Riemann surfaces or character varieties. So there's a correspondence via what we call non-abelian Hodge correspondence, and this is work due to Hitchins, Simpson, Donaldson, and Corlett. And there's the correspondence is with the space of representations that are reductive of the fundamental group of your Riemann surface into the group GC. So you take maps from the fundamental group of the Riemann surface into the group GC, and you take away you quotient by equivalences, and you take away the back representations, but that space is in correspondence with the moduli space of Higgs bundles. So any question that you may want to ask about character varieties, for instance, or this representation space, most of the questions, you can ask them from this perspective, at least the topological questions. And so you can understand, for instance, cohomology groups or Betti numbers in terms of one space or the other. And what people do very often is ask questions about the yellow space, but translate them into our Higgs bundle moduli space, understand them from there, and then go back here. So hopefully if you want to hear more about this correspondence, Carlos Florentino will be speaking later this week about this kind of procedure where you ask questions here and then you translate them. And we're going to keep that in mind, and anytime we ask questions today about the moduli space of Higgs bundles, we should remember that there is this correspondence, and we should ask the question, is there anything interesting happen in this yellow part? And what I'll show you later today is that indeed there are interesting things, and some of these branes that we're going to define will be related not just to representations of surfaces, like the case here, but also to three-dimensional manifolds. So we're able to put the dimension higher and start relating it to higher dimensional representations. There's something else that makes this moduli space very interesting, and that's going to be some structure that appears as a fibration, so it makes this moduli space into an integrable system. And this is, again, something that Hitchin realized back in '87 in his second paper in the subject. You can kind of start seeing the structure appearing here. We mentioned that these are SL2 Higgs bundles, and these SL2 Higgs bundles are parametrized by quadratic differentials. So somehow there are differentials parametrizing some moduli space of Higgs bundles. And this will translate into any other rank or group. So we're going to see that appearing for other groups. And that's what people call the Hitchin fibration. The Hitchin fibration is a fibration of the moduli space of Higgs bundles. So of our moduli space here is a fibration that takes the moduli space into a nice affine space that depends on the group, AGC I'm going to call it. And it's a fibration that makes the moduli space be an integrable system. So I'm going to call it H for the Hitchin map. Hitchin map. And the Hitchin fibration, so this makes the moduli space into an integrable system. So it gives integrable system. And the generic fibers, integrable system. The generic fibers are going to be abelian varieties, so compact abelian varieties with generic fibers, compact abelian varieties. So what Hitchin showed is that this map that one gets, and I'll tell you how the map proceeds, this map that he can define is proper, and the inverse image of points here give you compact spaces, and in particular, the ones that are generic enough give you compact abelian varieties as your fibers. So it gives what people call the abelianization of the moduli space, where you started with something that was non-abelian in the sense that it was a vector bundle of higher rank and a Higgs field as the classes, and you're sending it to something whose fibers are abelian varieties. And the way that you define it is as follows. You take an E phi, you take it in your moduli space, and you can do something because you started with matrices in the cases we're looking at. So if you start with a matrix, you can look at eigenvalues. And if you look at eigenvalues over each point of the Riemann surface, if I put here my Riemann surface, I can look at the curve of eigenvalues. So curve of eigenvalues. Curve of eigenvalues. Eigenvalues of phi. So the curve of eigenvalues of phi over each point of the Riemann surface, I have a matrix. I look at characteristic polynomial and take the eigenvalues, this curve that I'm going to call S, this is what gives me a point in the base. So every Higgs field that you take, you forget the bundle, you look at the Higgs field, you look at the curve of eigenvalues, and you send it to that curve of eigenvalues. The point will be generic if this curve is generic. So the point will be, you'll be in a smooth point if the curve is smooth. And you may wonder, what is the fiber then? What is this abelian variety? And the fiber is what's missing here. You have the eigenvalues, you're missing the eigenspaces. So you look at the eigenspaces on top of that curve. These will be line bundles on the curve, and that will be the fiber. So here, the fiber, so we said the generic fiber is the compact abelian variety. The generic fiber will be either the Jacobian of S or subvarieties, abelian subvarieties of the Jacobian of S. And we understand them as the eigenspaces of the Higgs field. So eigenspace. Space. So the eigenspaces are important as much as the eigenvalues. And that's what this abelianization is about. Now, there is this fibration, and so anytime we ask questions about the moduli space of Higgs bundles, we mentioned we can ask questions about the representation space, but we could also ask, how do things lie within this fibration? The fibration whose fibers are either Jacobian varieties or other subvarieties of the Jacobian, by looking at eigenvalues and eigenspaces. And this takes us to the last motivation that I want to give you, which is something that appears through our group. So through the group GC that we put there, there's something that's canonically defined, which is the dual group, the Langlands dual group of GC. If you haven't worked with Langlands dual groups, it's not a problem. What you need to think about is that if you have GC, you can define a dual group GC. So I start with GC, I can define a dual group GCL, which is the Langlands dual. Langlands dual. Just looking at co-roots of your group. And the cases that we're caring about, so we started with GLN, we mentioned, GLNC. And this is self-dual. You have GLNC. If you were to take, for instance, SL and C, you would have PGL and C. If you were to take the symplectic group, SPN, let me abbreviate there, SPN, you would get the orthogonal group of odd rank, so SO2n plus 1C, and the even one, the only one classical group missing here, SO2n, you'll get SO2n, so if cell dual. So this is the relation between a group and its Langlands dual. And what one can ask is, what happens if we require Higgs bundles to be for the dual group? Or equivalently, what is the relation between representations of a surface for a group and for its dual group? We can define the same moduli space, but now for the group that's dual. So let me put an L here, and now this is the moduli space of Higgs bundles for the Langlands dual group. We define it just as we did before with a vector bundle and a Higgs field, where we put the condition for the Langlands dual group. And we can look at the curve of eigenvalues just like we did before and get AGCL, looking at the curve of eigenvalues and looking at the eigenline values. What happens here is that the base of this fibration and the base of this fibration are isomorphic. So let me erase this yellow part and just emphasize that these two bases here that we have are isomorphic. So now you have two moduli spaces corresponding to representations for two dual groups that fiber over the same base or isomorphic bases whose fibers are toric varieties. And from the perspective of representations or Higgs bundles, there is Langlands dual groups play an important role. So a decade or so ago, or maybe 2 decades ago, Saslow, Strominger, and Yau, so Strominger, Yau, and Saslow, conjectured that the duality that's happening here, that's appearing here, it's an appearance of mirror symmetry, of the two moduli spaces. So the two moduli spaces appear as a case of toric fibered Calabi-Yaus, and the duality between the moduli spaces appears as a duality between the fibers of the fibration. We had 1 billion varieties in one side. We should be able to see in the dual moduli space a dual 1 billion varieties in the other side. So they propose mirror symmetry. Mirror symmetry is duality of fibers. Dual fibers. Just as 1 billion varieties, we think about Jacobians are self-duals, or prime varieties have a dual variety where you quotient by torsion endpoints, etc. Indeed, back in 2002, Housel and Thaddeus proved first for these cases that this is true, that the fibers are indeed dual. So this is Housel and Thaddeus in 2002. And soon after, in 2006, Kapustin and Wheaton and then Donaghy and Pantev looked at all of the other cases and showed that the duality is indeed a duality of fibers. Now, in most of these cases, I think in all of them, maybe Housel and Thaddeus have some comments for singular fibers, but generically, all of these results between dualities are for the generic fibers of the Hitching fibration. More so since the singular fibers, so the fibers over curves which are not smooth, or curves that are covers that are singular over the Riemann surface, those fibers are not fully understood. So we can't even start considering a duality, we can't understand the fibers themselves. So there are big open questions about understanding what these fibrations are over singular points, over singular curves S, and understanding what the duality does for those points. What I want to do today is I want to keep in mind these correspondence between fibrations, keep in mind the relation that we said was there between representations of pi1 of sigma into the group GC. So keep in mind this non-abelian Hodge correspondence. And I want to start asking questions about subspaces of moduli spaces of Higgs bundles and how they relate with these two motivational perspectives. How do those subspaces relate to representation theory or to Langland's duality? But I want to look at subspaces by classifying them in some manner first. So for classifying them, we need to first understand what we're going to classify them with respect to. So we're going to keep these here. Our AGC is our other base, and these are the two that are isomorphic. We're going to keep this picture, and we're going to be asking questions about these by classifying subspaces, which are branes. So from now on, we're going to look at branes and applications in the second half of the talk. I mentioned that the moduli space is hyperkähler, and the hyperkähler structure means that we have a lot of geometry appearing. So recall that the moduli space MGC is hyperkähler. One of the things that it means is that you have a sphere of complex structures that are compatible, and they produce for you compatible symplectic forms. So we can fix symplectic forms and complex structures that we can use. I'm going to fix, then, 3 complex structures, I, J, and K in this sphere, K complex structures. They satisfy the quaternionic equations, so I'm going to put K equals to I times J, and these square give us -1. They're complex structures. And we can take also the corresponding symplectic forms. I'm going to call them omega I, omega J, and omega K, symplectic forms. Symplectic forms. There are 2 things that you may wonder: how do we get the symplectic forms from these complex structures? If you start with your moduli space, you have a Riemannian metric there, where if you put each of these complex structures, you'll get your symplectic form induced. And you may also wonder, how are we fixing these complex structures? It's quite random, it would seem. You have a sphere of them. Why would you fix 3? So I'm going to fix 3 following the conventions from back in 2006 that Schaposnik and Witten used when considering this duality. And these are the conventions where the complex structure I is the one induced from the Riemann surface. So this is a complex surface we started with here, Riemann surface. And it has a complex structure that induces the structure on the moduli space. Then there is also another thing that we defined here. We took a complex group, so I'm going to take J, the complex structure induced from the group. And K is just I times J. So all of these structures are related. And now anytime that I look at a subspace of my moduli space, I want to ask, how does the subspace behave with respect to all of these structures? So if I give you a subspace, can it be a complex submanifold with respect to the structures? Or is it a Lagrangian subspace? So does it have the maximum dimension where one of my forms vanishes without being degenerate? If you haven't worked with symplectic forms before, these are 2 forms that are non-degenerate and closed in your manifold, in your moduli space, underlying manifold. So I want to ask those questions, and we have 3 complex structures and 3 symplectic forms. So we need a way in which we can recall whether things are complex submanifolds or Lagrangian subspaces with respect to each. And that's when we're going to start talking about branes. So we're going to take this wording from physicists and say that we're having branes when we take subspaces that satisfy some conditions. So I'm going to say that a Lagrangian subspace, a Lagrangian subspace and this is with respect to one of the forms. So I fix one form, and a Lagrangian subspace is an A-brane, and a complex subspace is going to be a B-brane. So a complex subspace is a B-brane. So now I mentioned in subspace, really it's submanifolds that we're looking at. And this is hand-wavy again, because branes from string theory perspective are not just subspaces, but they're subspaces which support subspaces in your moduli space which support a hyperholomorphic sheaf on top. But we're not going to work with that. It's already hard to understand the support of this object. So we're going to forget, and if you want, you can just think of the canonical or trivial hyperholomorphic sheaf on top of it. We're just going to remember the support. The second thing that we're avoiding here is we're not saying that all A-branes are going to be Lagrangians. So A-branes, if you care about categories, these are objects in the Fukaya category of a space, of the moduli space, and objects in the derived category of coherent sheaves. And those objects in this Fukaya category, there's other things that are not Lagrangians. But we're going to only take Lagrangians. And if you haven't seen this notation before, remember that Lagrangian has an A, and A-branes are A. So we have 2 letters for each of these 3 structures. We can be an A-brane with respect to omega I, omega J, or omega K, and we can be a complex submanifold, a B-brane, with respect to I, J, or K. So when we look at these things, the 3 complex structures that we have fixed here, we see that there is many options for our branes. Our branes will have triples of letters that describe how we behave with respect to each. So brane types will be, so let me put it here. The brane types will be triples of letters, for instance, B, A, B, 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 A, B, A, and AAB. So these are the 4 types of branes that one can have in a hyperkähler moduli space. In a hyperkähler moduli space, we'll fix in any your favorite hyperkähler moduli space, you'll fix complex structures, your favorite ones, and you'll fix symplectic forms, and then you ask, is a space Lagrangian or complex with respect to any of the structures? These will mean that it's a complex submanifold with respect to the structure coming from your Riemann surface here, but it's Lagrangian with respect to omega j and omega k. So it's Lagrangian with respect to the structure coming from the group that induces the symplectic form. This will mean that BBB will mean that it's complex submanifold with respect to everyone. So if you think about it, a point is a complex submanifold, or the whole moduli space, but if you, or hyperkähler submoduli space, but it's quite hard to understand other BBB branes and how do they appear. Here there's a Lagrangian submanifold with respect to the structure coming from the Riemann surface, or omega I, but it's complex with respect to this one. And because K is equal to I times J, as we mentioned before, there is no way you could have a subspace which is Lagrangian with respect to everyone. If you were Lagrangian with respect to everyone, your symplectic forms would need to be degenerate. So it stops there, and we don't have AAA. So the question we want to ask from now on is, how do we construct subspaces of each of these types? Back in 2006, when Witten and Kapustin were looking at this duality, in their electromagnetic duality paper, they considered the moduli space of Higgs bundles, and by the end of the paper, they introduced this idea of looking at branes in this triple of letters, and they saw that real representations into real groups, give you examples of BAA brane. And that was the beginning and the end of it there. And there's not much more being done for the next few years. So we've been asking with my collaborators, how do we get new examples? Once we get new examples of all of these types of branes, how do those examples lie within the Hitching vibration? How do they relate to representation theory? And how do they relate to mirror symmetry? In particular, because mirror symmetry from Strominger-Yau and Sassler perspective is the mirror symmetry of the fibers, but homological mirror symmetry from, say, the perspective of Kontsevich will give us a duality between branes. So not just the fiber, but these branes will have a duality. And the duality will be the following. So BAA branes will be dual type of BBB branes, so there will be duality here. And ABA branes and AAB branes will be self-dual. So these will be self-dual, these will be self-dual, and these will be of dual type. So anytime we produce a brane of one type, we can ask how does it behave with respect to the duality. And once we know that, we will know what the type of the dual brane is from string theory, but we don't know what the object is. So we want to ask that. Great. So I want to tell you how we can start defining these 4 types of branes from the objects we have. So in the moduli space of Higgs bundles. And the methods I'm going to introduce here today are methods that we've been working on for the last few years, and that by now are being generalized to other spaces. So for instance, the space of Nakajima-Quiver varieties, when you put a hyperkähler structure, you can add the same type of procedures to get branes. Or the space of frame instantons has the same properties, or K3 surfaces. So people have been working a lot on trying to extend this perspective to other spaces. And our goal will be to form spaces of each of these types, and in your head you can take your favorite hyperkähler space and try to do it. How do you form spaces that are Lagrangian or complex? The way we're going to do it is by adding symmetries to our system and ask for objects to be symmetric. And those objects that are symmetric are going to be giving us the spaces that we require. And the symmetries we're going to ask will appear through what we started with, our Riemann surface that we had here. So we had our Riemann surface here, our sigma, and we have a complex group. We have 2 complex objects. The first thing we can do is add real structures to those objects. So a real structure on the Riemann surface, so let me call it F. I'm going to put an F, which is a real structure. Real structure. And this is a real structure on the Riemann surface, which means locally it just looks like Z goes to Z bar. So you can just think of the complex plane in your head and think of complex conjugation. Z goes to minus Z, this involution, this is an anti-holomorphic involution on your Riemann surface. So anti-holomorphic. And the second object that we can do on the other complex space is our complex group, and I want to do the same. I want to add a real structure. So let me call it little sigma real structure. This means an anti-holomorphic involution that fixes the real form. So anti-holomorphic, fixing some G, a real group G of GC. So you can think of SL and C and reduce yourself to SL and R, for instance. Through those objects, we can define already 3 types of branes, and I'll tell you how. But I want to add one last thing, which is going to be another structure on my Riemann surface, and this time is a finite group action. So I want to add here acting some gamma finite group. So finite group. And a finite group will be different, its action, than a real structure. A real structure has, if any, fixed points. It'll have fixed points which are circles. So there'll be circles in your Riemann surface giving you the fixed points here. And the number of circles that you have and how they behave will give you the invariance. So these are going to be fixed circles. On the other hand, if you have a finite group action, your fixed points will be just isolated points. And these isolated points will give you the invariance. And it's through these structures that I want to define the branes. Before I forget, this is work that I've done either by myself or with Baraglia, who's a postdoc becoming a lecturer in Adelaide in Australia, and Sebastian Heller, some other papers, who's Heller, a postdoc in Tübingen, moving to Hamburg. And there are different papers. I can tell you which one is which if you're interested later on. So let me tell you what are these branes and how do we construct them. So we had 4 types, B, A, A. We had B, B, B. We had AAB and AB, A. These are the 4 types of branes, and through these different structures we can construct examples of each. And it's going to be as follows. When looking at a real structure on the group, the fixed point set, so real representations will give us BAA branes. So these will be from the little sigma, which means representations which are invariant under that involution. So representations that are from pi1 of sigma into the real group will give us Higgs bundles for the real group, and these will be BAA branes. If we take instead gamma equivariant Higgs bundles or gamma equivariant representations, where gamma is our finite group action, we'll get BBB branes. So gamma equivariant Higgs gives us BBB branes. Anytime you have a finite group action, we were able to show with Sebastian Heller that you get a BBB brane, and you can further ask questions about the fibration or questions about how it relates to representations in the sense of equivariance. The same for these branes. You can ask how do they lie within the Hitching fibration, what does Langland's duality do for you. One thing that I was able to show in this case on how they lie, these things in the Hitching vibration, is that many times you have also abelian varieties. So you have an abelianization appearing for some forms. But for others, you will never be able to do it, and you'll always have non-abelian objects. This is what we called, with Hitching, non-abelianization of Higgs bundles, which is really non-abelianization of BAA branes appearing in the moduli space. If you put the real structure on the Riemann surface, so we're missing an F there that we introduced, and a real structure on the Riemann surface will induce ABA branes. So ABA branes appear as fixed space of the induced action of F. So the real structure on the Riemann surface will induce an action on the moduli space, and that will go and give you ABA branes. And if you put both the F and the sigma, so if you put real structures both on the group and the Riemann surface, you get the last one. So here you'll get fixed, will be the space fixed by both your sigma, your real structure on the group, and your real structure on the surface. So what we're seeing here is that, at least for the structures, there are structures that induce as fixed point sets each type of the branes. And I'll tell you more about in the last 10 minutes of the talk. I'll tell you how these appear, which applications these branes have. If you know of other nice ways of getting Lagrangians, then that would be great to apply them here and get new branes in the moduli space. So I want to tell you a bit more about these 4 types of branes to finish off. And so you can see the type of questions that we can ask when considering branes inside the moduli space of Higgs bundles. The finite group action that we took here with Sebastian Heller, what we were able to see is that this BBB brane, at least in the case of SL2C Higgs bundles, you could have some abelianization, so you could have some prime varieties appearing. So it was quite nice in this case. And I mentioned some abelianization and non-abelianization of this one. Let me tell you a bit about ABA branes that come from a fixed point of the real structure on the Riemann surface, since it has some interesting applications in higher dimensional spaces and not just Riemann surfaces. So here we need to remember that on our Riemann surface we're taking E phi. So we're taking our Higgs bundle, our vector bundle, and our Higgs field pointwise. So something that's happening here is that your Higgs bundle has an induced action of F, and you're asking for the space of fixed Higgs bundles under that involution, and that's going to be your ABA brane. And we can ask, what is this ABA brane? So the first thing that we can say is that the ABA brane gives a real integrable system. So inside the Hitching vibration gives, instead of a complex integrable system, a real one. So it gives a real integrable system. And this real integrable system is a Lagrangian vibration, and the fibers are tori, collections of tori, and the number of tori in these fibers depend on the invariance of F. So all of the invariance of these will depend on the invariance of F. So with generic fibers, collections of tori. The number of which will depend on F. And there's something else that appears there, which is a relation with 3 manifold. So let me draw a very badly a 3 manifold here. I want to put a 3-manifold here, whose boundary is my Riemann surface. So I want to put an M here such that the boundary of M is my Riemann surface. And the type of questions I want you to have in mind are questions that you would find, for instance, in knot theory. So if you were looking at a knot and you put it inside a sphere and you take the knot away, you look at the 3-manifold that you get, and you look at the boundary, it's going to be a genus 1 surface. And the properties of these 3-manifold and its boundary are very much related to invariance of the knot. So in particular, if you ask which representations from or of pi1 of the Riemann surface extend to pi1 of M, so extend to pi1 of M, then from the knot theory perspective, if you were working with genus 1, you would be looking at the A polynomial, and the A polynomial would be choosing for you the things that extend, the representations that extend. But we want to ask this question for higher genus Riemann surfaces, so we're not looking at knots, but we still want to ask which representations extend from pi1 of sigma to pi1 of M, or equivalently, which Higgs bundles give you those representations that extend. And once you have them, what are the dual, Langland's dual spaces? To understand that, we need to understand which manifolds we can see in terms of our real structure. And one thing that you can notice through some procedures is that handle bodies can be written in terms of real structures. So if I have a handle body, then I can write it as a quotient of our Riemann surface times an interval, minus 1, 1, a quotient by the involution. So x, t, a point x in the Riemann surface and t in the interval, I'll send it to f of x minus t. So there's a way of finding the real structure that will take you to that representation of the 3-manifold. And once you have it, you ask this question and we'll answer it from this perspective. So the things that will extend, so we're going to ask which ones do extend, and the answer will be the Higgs bundles, or the representations whose Higgs bundles, whose Higgs bundles are in the ABA brane, but not just that. In the ABA brane, such that, and there's something else, and I'll finish off the talk by telling you what this something else is. So the something else is an invariant that appears naturally and that somehow has to do with the other types of branes that I introduced too. And it's an invariant here that appears from our object, our involution F. What's happening here is that in your 3-manifold that you have and your boundary, so we're going to care about the boundary now, and we're going to care about the Higgs bundles that we had. So this is a vector bundle, and remember we had a Higgs field that sent E to E tensor with the canonical bundle, or otherwise the cotangent space of our Riemann surface. This was our Higgs field. And we're asking for objects that are invariant under our involution, so objects that are sent to themselves or invariant under isomorphism under the involution F. So the lift of F from the surface to here. What this means is that if you were to take any point that's not fixed, you're looking at the class being fixed between those points. But if you look at this part, if you look at the red part here, this red sorry, that was dreadful. We're almost done. If you look at this red part here, then what we need is the vector bundle to be sent to itself or minus itself, or its dual. So we only have two options. For each dimension of our vector bundle, we need to take, it's like if you had a line bundle here, a one-dimensional space, on a fixed point, it has to be taken to itself or to its dual. So we have a choice of plus or minus 1 for each dimension, of E. So you look at your vector bundle on a fixed circle, and for each circle, on each fixed circle. So for each fixed circle, you look at each dimension and you have a plus or minus 1 that you have to choose. And you wonder, what is this object? This object, in fact, defines your class. So this is the K-theory class of E, the vector bundle E, inside the twisted K-theory, equivariant K-theory of the Riemann surface under the involution that you applied. So this is under the Z2 action of our F, we have a class of E. And this class is going to be fundamental. So the things that extend are the Higgs bundles, or the representations. Higgs bundles are already in our ABA brane, but not just any. They are the ones that have the class of E being trivial. So we can identify all the representations that extend from a boundary of a three-manifold to the three-manifold itself as part or components of this ABA brane. And these components are selected to you by looking at this class. If you cared about the other types of branes, instead of looking at this equivariant K theory, what you're doing is you're looking at KO or KR theory. So the real, you have different K theories for each of the branes, picking for you the different types of objects inside each moduli space. So I should finish here. Thank you very much.